Exercise 36. Prove that if G is a profinite group, then consider the category denoted by MODJ, which by our definition is the category discrete G modules. Has sufficiently many injectives. Okay. Proof. Firstly, let's fix some notation. So this category consists of discrete G modules, which means recall that there is a continuous action where there is profinite topology on J, and on M this is discrete topology, and this actually is continuous. This map is continuous. The topology on the left hand side is product topology, and on the right hand side is discrete topology. Okay, and in contrast, we have this category of abstract G modules. So again, topological opening groups endowed with continuous action, but not necessarily discrete topology on M. Okay, so M is within topological groups endowed with G action, which means have this map again continuous. Okay, we're going to prove that in the category of discrete G module there are sufficiently many injectives. And actually, what we know is that, another thing that's a sub fact or sub exercise, is that, so before the proof, some notations, some remarks. The fact is that the category of abstract G modules is category equivalent to the category of modules over the group ring C bracket J. In particular, any R module has enough injectives, so it has sufficient many injectives. So this exercise basically is knowing that the abstract G modules have sufficiently many injectives. Do we know that the discrete G modules also have sufficiently many injectives? Okay, so start proof. So let's take any abstract G module. We associate with it a submodule M dot are defined to be all those points fixed under some open U. So put a remark the middle. So this means open subgroups. If we do M with discrete topology, then this M delta is the maximal submodule of M such that Gx continuously so why this is the case? So this could kind of following this exercise 34 and 35. So basically notice that so the maximum is in the sense of inclusion theoretically. So the first point is that notice this M delta is the union of some open subgroups. U takes fixed points, which means by exercise 34, 35, this is continuous, right? And so this is so I'm seeing something. Of course, if M is already a discrete G module, which means you already have continuous, actually you don't have to reconstruct something. What I mean is if you start with abstract G modules, then we don't know this so let me say it again. So basically what we really care about is, let's say, start with any discrete G module, let's say A. We want to show there has enough injectives. The way we do it is this discrete G module is a subcategory of G module, abstract G module. Let me call this abstract G module G mod. Okay, and then because this has enough injectives by our factor sub exercise, so there exists some I injective object in this abstract G module category. What we want to do is we want to show that we could construct an I delta, which is a submodule of this injective I, and it factorizes through this I delta. And this I delta we want to show moreover, it is here. And so this proves that in the category discrete G modules you have enough injective. This is the basic idea. So what we are doing now is we'll kind of first explain this procedure. Start with any abstract G module, how you construct a discrete G module. As application, we'll apply it to injective ones and show that injective ones I construct a discrete G module I delta, and it's still injective. Okay, we'll see that. To summarize, we already proved that we have construct for any abstract G module M and associated discrete G module M delta. And kind of this remark is more than what we require. This remark is also saying that this is not only a discrete G module, but the maximal submodule of M such that Gx continuously. So discrete, of course, it requires this G action is continuous, and we claim that this M delta is the maximal submodule such that Gx continues, because why it is the maximal. So if m prime containing m is a discrete G module, then by exercise 34, m prime will equal to the union of all its fixed point, some open U in J. In particular, this would be contained in the union of U open J of M under U, right? And then this is our M delta. And so whatever submodule that is discrete would be containing this M delta. That's and this is maximal one. Okay. Now let's say that you could think of this as a sub-exercise, but I will give you the proof anyway. So let me say, notice that every J homomorphism from a discrete J module and to some M factored through M delta. Okay, the proof would be that, so you have some Frobenius, not Frobenius, some more homomorphism G homomorphism, which means J equivalent from some discrete module N to M. And we have this M delta is submodule of M. Does it factorize, which means is phi of n contained in some m fixed by U. So let me first put m delta for any n is phi of n containing some m U of n right? That's the question. Does they factor through? So by definition, so phi is G equivalent means J of phi equals phi whatever J, which is the same as saying that J phi J inverse of n. Let me one more step. J phi J inverse equals phi whatever J is equivalent to say J phi J inverse A equals phi of A. Let me put n maybe because this is in n. For any n in n, J in J, right? That's what we know. So the question is, how about this? Let's look at this image of phi n. Is it containing some un? So firstly, n is a discrete module. So in particular, there exists some un such that so we don't really need this big un. So what we need is that for any n, so let's look at this is what we want. So for any small n in big N, we have this stabilizer of n, which is by definition of discrete G module, this G action being continuous. Then by exercise 34, this is equivalent to say the stabilizer is open in G for any element small n, this discrete G module big N. Right, so now let me show that I claim this is enough. Phi is contained in M stable line fixed by Gn. Why this is the case? So let's check. So we have to show that for any small j in Jn, J phi n equals phi n. This is what we want. But notice that this is also, because it's equivariant, this is also J phi of n, and this is by definition J phi J inverse of n. But J is in stabilizer of n, and so this is also J phi of n. And so this is indeed equality. Okay, so this shows that it always factors through m delta. Nice. So with this exercise, what can we say? So let's come back to our starting point. So notice that, let me put again a remark. Notice we only require m to be discrete in the above exercise when this factorized through, sorry, this is our notation from n to m. Only require this n to be discrete. We don't need this to be discrete. This could be abstract one. In the above sub-exercise of factorization. Okay, so now let's come back to the proof of exercise 36. Start with any discrete G module M. So because by our sub-exercise at the beginning there exists some injective not in this discrete G module but in abstract G module. But then you consider this out delta. This is in the discrete G module. I did factorize through this, right? So left to show that this out delta is injective in this discrete G module, provided that it is I is injective. I is injective in abstract G module. How do we prove that? Just check by definition. So in the category of discrete G modules, let's see, suppose we have injective. In the category of discrete G modules, for an arbitrary map from A to this out delta, we want to show that there exists unique map vector through it, right? So what we know is that this is also a good thing as a subcategory of abstract G modules. So there exists unique map from B to I. So the question would be, would there be a factorization? So this is the second sub-exercise. You have J homomorphism phi. Because we're in the category of G modules, so the homomorphism maps, the arrows are G equivalent maps. Factorize through L delta, because this is discrete. And we don't need the second one to be discrete. And so this shows that this I delta is injective, and so we are done.